No, it's just the $10. There's also an incentive to pay early
There is.
Yeah, you get an
that you
extra
get
ticket.
thrown in for an extra ticket for a prize.
Oh yeah, isn't it by tomorrow?
If you give it by tomorrow.
I give it to my teacher.
Yeah, you can either give it to me or like to the office. It's fine too.
Will I still get the incentive if I give it to you in 5th period?
Yeah. I mean, I was gonna take it over during 4th, but when you sign in, you could also give it to them.
Oh, that's true.
And I could just write a note that you're bringing it when you come
That's
or whatever. All right, max, min, and inflection points. Curve sketching. All right, case 1. Functions that are differentiable everywhere.
That's
Sounds
case
like a
1 or
moose.
Case I.
1I, Roman numeral.
Roman, I forgot those.
If it would make you feel better, I can write it like that. Haven't used Roman numerals in a hot minute, huh?
Yeah.
I was never a Roman numerals person. I was always a bullets and dashes person.
Of course. I was always,
So when Miss Patton was like, "You have to write an outline with Roman numerals," I was like, "Is there another
Yeah.
option?"
why?
Like, I know it's the same thing, but it just really irritates me. I don't know why. All right, the first thing, we find y prime and y double prime. Two, find all critical points of y. And how do we do that?
If it's
Seeing what like doesn't
see
work
what
or like what
value
makes
is equal
it
to
doesn't work or
0.
something.
Which ones? From what? From the original?
Oh.
From the derivative? From the second derivative? From what?
The
First
original.
or
Oh.
The first derivative. Then we use those points in the original.
Oh, okay. I still don't really understand the first one.
For all x, for which y prime is equal to 0. So it's also where they do not exist, but for this, we're just looking at the ones where it equals 0. And just more of a informational thing for you. At each of these x values, the tangent to the curve is horizontal. All right, so this next thing is going to lead into the second derivative test as well. So basically what we were doing yesterday is we were finding the critical points. We were plugging those into the original and finding out what the max and min values were. And we were like, well, if we only had one, we had to go through and we had to use a different method to find it, right? But technically what we were doing is we were looking at all the values and we were saying, okay, what's the lower one? That's got to be the min. What's the higher one? That's got to be the max. So now we're going to look at actually how to use the second derivative test, which I kind of showed you like briefly yesterday, but now you'll actually have it in writing to make it a little bit easier. So let's see. Be a number for which y prime is 0. So basically, it's a critical point. Then we're going to check the sign of y double prime at C. So then, two scenarios. If y double prime of c, so if we evaluate the second derivative at that point, is greater than 0, then c is a local min. If y double prime of c is less than 0, then c is a local max. This is the second derivative test for extrema. Now, what scenario have we not accounted for?
If they equal 0.
Yeah, if it equals 0. So if the second derivative evaluated at the point is equal to 0, so we need to look at what that is. If y double prime of c is equal to 0, the second derivative test fails. And we must use the test in the next step. So basically, we go on to step 4. But if we had gotten to that point and it was good, then we would have been done with that at that point. So if y prime of c is equal to 0 and y double prime of c is equal to 0, so if the first and second derivative are both equal to 0, we are going to check the signs of y prime as x increases through c. If y prime of x is greater than 0 for x less than c, but y prime of x is less than 0 for x greater than c, then where there is a tangent line as x increases through c, there is a local max. So then I'm not going to like write the whole thing again, but if the situation is reversed, so that y prime changes from negative to positive as x increases through c, Then C is a local min. Now, normally the first, the second derivative test does work, so this doesn't occur as often. We won't have to deal with that as much. All right, then there is a fifth step. Actually, do I want to? Let me give you a visual of what we just wrote first before I do step 5. Might make it a little easier.
How much room will we need for the visual?
There's 4 graphs, but they're not. I mean, they don't have to be big, but I'll write like a little thing underneath of them. Okay. So if we had a graph like, oh, that's too big. Or one like, I'll do those 2 first. All right, so basically we've got, I'm going to draw the lines like this. One there. Got one there. One there. Y prime changes from positive to 0 to negative. So C is a max. And C would be just like right here in the middle. So the tangent lines are like the kind of like the graph of the derivative almost. So it's going positive, 0, and then negative, and that's where they're getting that from. For this one, let's see. All right, that's going to be C again. We've got one there. There. So in this one, Y prime changes from negative I'm technically missing a line here. I'm just gonna draw it small. To 0 to positive. So C is a minimum. All right, so this one, the sine of y prime is positive, then 0, then positive again. So there is no max or min. So this one's kind of just the reverse of the previous one. The sine of y prime is negative, then 0, then negative. So no max or min. All right, step 5. Find all x values where y double prime is equal to 0. These are possible points of inflection. If C is an x and the sine of y double prime changes from positive to negative or negative to positive as x increases through C, then C is an x-coordinate of the point of inflection. If the sign doesn't change, C is not a point of inflection. All right, I'm gonna look at an example. You can see how this actually works. Find any max, min, or inflection points on the graph of f of x is equal to x cubed minus 5x squared plus 3x plus 6. So we'll go through and follow each step individually to kind of work through it so you can see what that looks like. So the first step was to find y prime and y double prime. So I need to take the first derivative of this. So step 1, y prime. So what would y prime be? Yeah. Yep. Then I need the second derivative. Six x minus 10. So now we need to find all the critical points of y, so for all x for which y prime is equal to 0. So we need to set y prime equal to 0 and solve. So step 2, we're going to set 3x squared minus 10x plus 3 equal to 0. How would I go about solving that? Back to algebra.
Factor?
Possibly, but there's an easier way. So yes, factor. I was saying easier way to him because he said quadratic formula.
Oh.
I would rather factor personally. All right, how do I factor? Throwing it back a little bit.
So you want to find two terms that'll equal.
Yes.
So
So you gotta multiply the.
So I need
Negative.
factors of 9.
-9
Yeah.
and -1.
Yes, that add up to give me -10. So 3x squared minus 9x minus x plus 3. Now what?
Separate them.
I'm making sure we remember how to factor, y'all.
So out of that first piece, you can factor out 3x. And then out of that one, you can factor out negative 1.
All right, success. 2 parentheses match.
Oh yeah.
Oh,
I make them match whether they like it or not.
Yeah, I've had a few people do that on tests, and I'm like, there's no way. There's no way you got that from
I really just. Oh my gosh. Wait, you know how like we were all going like this in anatomy yesterday?
yeah.
It kind of hurts right there now. I think I did it too much.
Why were y'all
going
doing
over the
that?
muscles?
Oh.
Because this is the platys muscle.
It is. I didn't learn
Remember
which
that?
one
Why
it
do you
was.
remember that?
It sounded like platypus.
I was thinking of Harry the Platypus the other time. But so
What?
now we set them both equal to 0. So then it's x equals 1/3 and x equals 3. And or whichever one it is.
Yeah. All right, so what are these?
Critical points.
Critical points.
I wasn't done writing, so I didn't even like take a chance.
Very.
Stealing your thunder.
Mm-hmm.
All right, step 3. Let C be a number for which y prime is 0, so that's what we just found. We're going to check the sign of y double prime at C. So we're going to take that number that we just got,
Mm-hmm.
Okay, and we're going to plug it into the second derivative and see if it's greater than 0, less than 0, or equal to 0. And we're
Okay.
going to hope that it's not equal to 0 because that just needs more work.
Seriously though.
So we're gonna have to do it
Just
'cause
twice.
There's two numbers.
Yep. So we're going to have, just for reference, so f prime of 1/3 is equal to 0. And that's all I'm redoing is reiterating what we just found in step 2. That the derivative evaluated at that point is equal to 0.
Mm-hmm.
Okay. So the second derivative at 1/3, I want to know basically with the sign of it, what is it? So I'm going to plug in 1/3 to this. So 6 times 1/3 minus 10. And all I care about is if it's positive, negative, or 0. I don't care what the number is. But
Did you try to make that a 6?
yes, it just
okay.
skipped.
Yeah.
I don't know. I looked down and I was like, something's not right. As like you said that, I was like, oh.
Like there's a number missing.
So 2 minus 10 is
Negative.
-8. So that means that the second derivative at 1/3 is less than 0. So what does that mean?
It's max.
So there's a max there. Now, because of the way the book does this, I'm going to write it this way. There is a local max at, or here, I'm going to do it in red so you can see it. The point, because sometimes it'll ask where the actual, like the point is for it, at 1/3, because that was the x value. And then f of 1/3. Okay, that would be the y value. So that would be the original equation at that value is where the max occurred. Which we'll go back and figure that out in a minute. All right, so that's the first one. So I'm going to now do the exact same thing, but for 3. So I'm going to write it the same way just for visual reference. So the derivative at 3 is equal to 0 according to what we just found up top. So the second derivative at 3 is equal to 6 times 3 minus 10, which is what?
8.
So the second derivative at 3 is greater than 0. So what does that mean?
It's a local min
There's a min
at
at 3 and
Just
f of 3. So then we need to, the book would want you to actually find those values. So we would need to go back and plug it in. I'm going to save some effort. This one is 1/3 and 175 over 27.
Oh, like plug it into the original.
Yeah.
ew.
Yeah.
And what would that be finding?
That would be actually finding the point on the original graph. Because what we did in these graphs here in step 4, which we don't need step 4 because we didn't have any that were equal to 0. None of the second derivatives were equal to 0. But what's happening here is these graphs, these lines are basically showing you the derivative. The blue part was the original equation.
Okay.
So to find the max would have been at C and whatever that y value was. F of C. And this one, again, just to save you from having to do it, it's 3 and -3 is what it comes out to be. All right, so I'm just going to note that step 4 is unnecessary. If I can spell. For this problem. All right, finding the points of inflection. So step 5. Find all x values where y double prime is equal to 0. These are possible points of inflection. So we're going to set the second derivative equal to 0 and solve and see what happens. So 6x minus 10 is equal to 0. So x is what?
10 over 6.
Which reduces to
5 over 3.
5 over 3. We would need to kind of look at the graph to see what's happening in terms of the negative and positive. Or if it's going from negative to positive or whatever. But as we go, as x increases, basically if we picked a smaller x value and we see what's happening. So like if we did like 0, we would get negative 10, but if we picked something that was like bigger than that, so like 2, it would be positive, so it's going from negative to positive, if that makes sense. Like if we just plug in values to see what's happening. Now that's probably not the technical calculus way that we should do that, but it works, so might as well. It's like we used to not be allowed to graph parabolas by just like plotting points, but it's like way easier
Yeah.
to just do that, and so like we had to learn like the real method or whatever, and I was always like, why? Like there's such an easier way. It's kind of like this, like use the easier way. So basically I'll just show it. So if x is equal to 0, then this would have been equal to negative 10, but if x was 2, then it was a positive 2, so this goes from negative to positive. So this changes from negative to positive as x increases through 5/3. So there is an inflection point. And to find that, we would evaluate the original equation at this point that we found. So we would have the point of inflection would be at 5/3 and f of 5/3. Come on. Which happens to be 5/3 and 47 over 25. No, 47 over 27. So based on all the information we have, we could graph this now.
Would that be plugging it into the second derivative?
This one was back to the original.
Oh, okay. So
All of these are the-
47 over 27.
Yeah.
Okay.
47 over 27 is the result of plugging it into the original.
Okay.
I was just saving from having to do the work. But so you could then, with all this information that we have, we could sketch the graph, okay? You would have a point at 1/3 and 175 over 27, which would be, you know, somewhere way up here. We have a point of inflection at 5/3 and 47 over 27, which is going to be somewhere in this vicinity. Probably like much lower, but anyways, down here. And then we knew we had a point at 3 and negative 3. So down here. And so because we know what happens, we know that the 1/3 and the 175 over 27 is a max. We know that the graph is going to do something like that, and we know that this point's a min. And so without your calculator, you just graphed that original function that you would probably not have known how to graph otherwise. Which I'm sure you just really wanted to know how to do.
That was just so interesting.
I've been wondering for a while.
We'll look at an example tomorrow because we're almost out of time of what happens if there's one where the second derivative test fails and what that next step would look like. That step 4 looks very similar. Yeah, that step 4 looks really similar to what we just did in step 5 as in terms of checking as we go through a point. But just showing how to like look at it and see then if there is or is not a max or a min. And then there's one more case, and then we'll actually go back to examples from the book to finish up the section. So we should finish it up tomorrow. Which this section was slated to take 5 days, and so by the time we're done with it, it will have taken 5 days. Because we did the one day before Christmas that we forgot about.
Yeah.